So quantum computers are a different mode of computation. They use a kind of different physics and different science. And what they allow you to do is find shortcuts to reduce problems that are super hard in classical computers to problems that are solvable. So it's like an NP reduction. You take this thing like crypto, for example. So how public key crypto works is that you have a really hard math problem that allows you to basically construct a public piece of information that everybody can see, and then you keep a private piece of information, which is a trapdoor. And to discover that trapdoor and that really hard thing, the only way you could do so is either know it already, so you created it yourself, so it's your secret key, or solve a very hard problem that is known to be very hard or suspected to be very hard. Well, it turns out that quantum computers are really good at finding shortcuts through the magics of special algorithms like Shor's algorithm and so forth. And they allow you to discover that piece of information without having to tackle that very hard problem in the traditional way. So this is really scary because how we've constructed crypto kind of relies on those foundations. And when you remove these very hard problems and you make them solvable, then all of a sudden with a quantum computer, you could start breaking encryption. So the good news is there's a whole class of algorithms that are quantum resistant, like hash-based crypto and lattice-based crypto and learning with error, super singular isogenies, and so forth. And there's tons of mathematical primitives that are believed to be quantum resistant, or they just kind of make back of the napkin sense for that. Now, we could introduce those primitives into Cardano at any time. And we've even built a bespoke one using XMSS with a KES with Peter Schwabe. Now, the problem is that those algorithms carry trade-offs. Generally speaking, they're not optimized. They're significantly more resource intensive, so the keys are much larger. It's harder to verify them, and they rely on primitives that are not as well understood. And as a consequence, they could potentially not be secure. There could be vectors of attack. Whereas the primitives of elliptic curve crypto and RSA are extremely well understood, and they've been around since the 1980s and 70s, respectively. So you never get something for nothing. You always have a trade-off. Now, just the public key crypto is not enough. You also have to model your way you generate random numbers, and you have to model the operation of your system from the perspective of what's called a quantum adversary. That modeling effort is underway, and we have written some papers on it, and we are looking at things like potentially doing a post-quantum VRF, that's how we generate random numbers, but getting all of these things done in a way that mitigates their trade-offs and enhances their security is an exceedingly difficult project, but it's not necessary in the short term, like Basho. So what we'll do with the renewal when we ask for it is include a quantum research agenda so that Cardano is end-to-end quantum resistant. And we'll make sure that all those papers get written, the testing gets done. And since we're doing quantum stuff, we'll try to introduce not only post-quantum crypto, but quantum crypto. So post-quantum crypto is crypto that helps you defeat the existence of quantum computers. Quantum crypto uses some of this newfound weird stuff in the quantum world to do crypto better. Like, for example, we wrote a paper called one-shot signatures, which means it's almost like the mission impossible. The signature self-destructs after you read it. So you can only use it once, and by the laws of physics. So there's really cool stuff that we can push down the pipe. And it's not necessarily today, but it will be necessary in the 10 to 20 year time horizon if we look at the evolution of quantum computers. So it is certainly something that we should, as an ecosystem, start planning for and gracefully add in once we've annihilated as many trade-offs as we can. The good news is we can piggyback on work that the US government is doing and other governments are doing because they have a lot of secrets they'd like to keep, and they're just as vulnerable to those secrets being revealed if crypto doesn't work as we are. So some of the world's foremost engineers and intelligence agencies and Defense Department people are doing a lot of work on algorithms and fundamental research to try to get proper protocols. And the good news is most of this work is in the open domain. It's open source. So we can borrow that and use it.